Hi there. Let's talk about parallax. This is a confusing topic for astronomy students, even though it is something that you can understand using normal terrestrial references. So what I've done here is I went to Stellarium and I searched for Pluto, and I've sort of zoomed in so you can see Pluto and you can see the background stars. What I want to do is I want to change the day here. So I went forward a few days. If we go backwards a few days, you can see that the stars kind of move a little bit, but Pluto is zipping along a lot in between each particular image. The reason is parallax. So imagine you and your friend both went to the store, and you both went to, say, a Target, as if we could actually go into a Target and walk around. And you're both wandering around and you get separated. And you know your friend's still there somewhere, but you're not right next to them anymore. Now imagine you have a third friend who's on vacation in, say, Mongolia. That third person isn't in the target with you, isn't right next to you, and the difference between how far you are from your target friend and how far you are from your Mongolian friend is pretty gigantic. That's what it's like for us in Pluto. We're basically the two people in a single target. We're not right next to each other, but we're more or less in the same area, at least compared to our friend in Mongolia. The stars are unbelievably far away. If we use the astronomical unit, that makes good sense in the solar system, it becomes pretty unmanageable when we get to the distant stars. Instead of a dozen or maybe a few hundred, it can be thousands, tens of thousands, millions, even billions. So the differences in scale really cause a bizarre impact on observation. That's where parallax comes into play. So you can see Pluto is zipping along from day to day to day. So imagine in this scenario, we've got a drone looking down on a road scene. Here we are driving along on the road. The red X is our car. And here we are looking out the window. So this is us looking out the window. This view over here is a drone top-down view. And as we are approaching the edge of the road over here, the sailboat, which is in the quote-unquote foreground, this is Pluto, this is Earth. The distant stars are like this shore over here. When the car is at different points along the road, the boat is going to appear to move relative to the background stars. In fact, if we had a laser pointer and we could shoot it, there would be a line going from where the car is now through the boat to the distant shore. And if we come over here and we do it again, notice that there's some angle between the two. The closer an object is to you when you take the two measurements, the bigger the angle is going to be. The bigger the angle, the closer the object. The smaller the angle, well, we're not going to be able to move the sailboat, so that metaphor kind of falls apart. But the smaller the angle, the farther the object must be. So you can see here that the distance between us and the sailboat is really going to affect how it's going to appear to move against the background stars. And I would touch on, let's do a little math actually, instead of doing another simulation. So I try to draw a little cartoon version of what I'm talking about here. So this is the drone's eye view of our solar system now, okay? And specifically, here's Earth in September, here's Earth in March, here's Earth in December, here's Earth in June. I left out June because it was kind of in the way of my lines. And here's some space rock we want to see. Maybe it's outside the solar system, but not as far away as, the distant stars. And we want to figure out how far away it is using parallax. Well, how do we do that? The trick is to take a picture of it when Earth is as far apart from your previous observation as you could be. So if we use the Earth's orbit, instead of the road being, one end of the road down there, the other end of the road down there, one of the things we can do as observers is use the Earth's orbit as a way to make our two observations as far apart as we can get, at least from the standpoint of living on Earth. So we take a picture in March of, here's our laser pointer pointing up towards the object and heading off into the stars. Here it is. Here's our little space rock, and you can see the distant stars. If we wait, we go through June, we get into September, and we take a picture again. So it's now been 6 months from here to here. That's as far apart as observations can get. And we take another picture, we'll see that the rock has moved. And what we can do is literally measure the distance between them. And that distance is going to be the angular distance right there. This angle right here is called the parallax angle. Parallax angle. And if we measure that with two observations, parallax angle is going to be equal to 1 over the distance. And as long as we use the right units, this is the entire equation. The trick to the units, by the way, will be, down here, these need to be in something called parsecs, which I'll save for another video. And over here, the angle needs to be measured in something called arcseconds. And again, I'll save the units for another video. But as long as you have your angle measured out in arcseconds here, and as long as you're willing to deal with this unit of parsecs, then the equation is just P equals 1 over D. That means all you need to do is measure the angle in arcseconds, and we can immediately find the distance. Distance will be 1 over P. So that's why we use these convenient parsec units. I hope that at least clears up a little bit about parallax. The most important thing is, the closer an object is to the observer, the bigger the angle will be. The farther away they are from the observer, the smaller the angle will be. So if you are asked a question about parallax angle and distance, a big angle means small distance. A small angle would instead mean that it must be pretty far away. Okay, I got a phone call right in the middle of that. I hope it still works. We're going to stop there. Hope that works.